So what we're going to take a look at today is a little bit of graphical kinematics. Now, it's a different way of approaching kinematics. Of the things that we've looked at already in class are solving kinematic equations and problems using our kinematic equation sheet. Now, one of the things that I don't have written in here, which you should keep track of, is these kinematic equations that we use in class are only applicable when acceleration is constant. We're going to find that with graphical kinematics, many times we can work with stuff that doesn't have constant acceleration, so that's one upside of it. The downside is you have to have things kind of graphed out, and sometimes you have to have a lot of extra information. And that being said, let's see how we can work with graphs. First off, we need to talk about naming. Now, this is something that I've talked about in class before, but let's make certain we're all on the same page. This is a position versus time graph. Now, the first one, whatever name comes first in the title, is what is on your vertical axis, your y-axis, if you will. But I'm going to try and say vertical and horizontal, because sometimes we'll have x on as one of our variables, sometimes we'll have y, and they may not end up on the classically x or y axes. So this is horizontal, here's vertical. First name, position, whatever comes first is on your vertical axis, versus whatever is on your horizontal. Now the thing about graphical kinematics is pretty much everything is always versus time. So most of the graphs, if not all of them that we work with graphical kinematics, you're always going to have time as your horizontal axis. Now, one of the things that I want to bring up is sometimes in lab, you may have it if you stick with that whole dependent, independent variable thing, where time becomes your vertical axis. I wouldn't recommend that, and we're going to see why as we go forward. Now we have position in meters, and we have time in seconds, which is what I've got set up, and those are the SI units. They're our preferred ones. This is a random graph that I have put together of the motion of some object. Now, one of the things that I'll point out here is you'll notice that 0 is partway up my graph, and we also have -1, -2, and -3. When you're dealing with position, we could say that right here is my origin, x equals 0, and if I move to the right, this is +1, +2. I'm going out of frame now, probably. +1, 0, -1. The negative means because position can be a vector, our displacement, delta x, is a vector, the negative keeps track of which direction in our one dimension. So we can either go to the right or to the left if it's in the x direction. We can go up, which is positive usually in the y, or down, which is negative. But we can have negative values for our position. All right. The nice thing about these graphs are you can read them immediately based on whatever they are. So it's position versus time. So I could say at time equals 7 seconds, time equals 7, we're at a position of -1 meters. That's where the object is. At time equals 5, we're at a position of 7 meters. I'd act that out, but I'd end up off frame and far away and walking into my computer, actually. So at time equals 1, we see that we're at a position of 2. You can read the position and the time working together at any given point for your graph. So that's a great way to represent information. But the reason why we choose specific graphs is what else we can tell. Now, one of the things that we're going to want to look at is going to be our slope. Now, we've graphed many things here in class, and one of the things that we're constantly looking for is the slope. So if I look for the slope in this section, what I can do is, well, we find slopes by using rise over run. The slope will be equal to our rise over run, which another way of writing that is y1 minus y0, or y2 minus y1, over x1 minus x0, or x2 minus x1. All right, well, we've got 2 points here. Down here, I've got this point, which my x is 0 and my y is 0, so this is 0, 0. And up here, I've got my x is 1, comma, my y is 2. So you can keep track of that just like you do in math classes. Now, one thing that we're going to bring up in just a moment, in fact, let's go ahead and play with this, and then I'll bring up the important thing that I want to add in just a moment. So if I find my slope right in here, I would take y2, which is 2, minus 0. So that's going to be 2 minus 0 over my run x1, 1 minus x0, which is 0, so that's going to be 1 minus 0. I end up with 2 minus 0, 2 over 1, that gives me 2. Hooray, slopes. But I've mentioned this many times in class, this isn't just 2. This is a graph of something. This is 2 meters. This is 1 second. Seconds, meters. Meters are my y values, and seconds are my x values. So it's not just the numbers, it's the actual value that we're looking at. So I end up with not just 2, but I have 2 meters divided by second, meters per second, which is the units for velocity. What we've actually found here is something technically called the average velocity, because we're just saying it is here at 0, 0, and it is here at 2, 1. We don't know exactly what happens in between. So in the course of 1 second, you may have had them move a little bit slow and a little fast, or you might have them move the same speed the entire time, or you might have them move really fast and then slow down some. In real life, you've probably got it where they're doing some combination of all those things. For the most part, when we're working with this, we say that this is the velocity that it has during that period. Although that may also be just finding, on average, how fast it was moving during that time. That being said, what we're looking at here, we would say that our speed, or our velocity, I should say, between time equals 0 and time equals 1 is 2 meters per second. Now, I say specifically velocity. I corrected myself a moment ago when I said speed. Let's take a look at this. Let's look at a different section. Let's go to, well, let's try this real quick. Let's try in here, between these points here. So I would have, we're at 3 meters. We're at 3 and 4, so that's 4 seconds. Minus, over here we're at 3 meters and 2 seconds. Well, that gives me 0 meters divided by 2 seconds, but that's just 0 meters per second. It's not moving. And that actually agrees with what we've got. It's at 3 meters, and it stays at 3 meters. So it means it's not moving. Then we have another velocity in here. You could find that with your slope. But why I keep saying velocity? Let's look at this one. This one's a little weird. My second point is over here. It's at 6 and 2. So we've got 6 seconds, 2 meters. And up here we've got 5 seconds and 7 meters. Now remember, this is my second point. This is my first, at least what I'm looking at here. And so my final y, let's see, 2 meters, 7 meters. Yeah, that is quite a bit of movement. So I'd have 2 meters minus 7 meters. Here's my second point, subtracting my first point's values, divided by, well, 6 seconds minus 5 seconds. I end up with negative 5 meters divided by 1 second, negative 5 meters per second. This is why I say it's a velocity and not a speed. The negative means something. We were at 7 meters, so I'd be way off over here, and then a short time later I find myself at instead about 2 meters. I'm moving this way, I'm going to the left. This is a velocity, not a speed. The negative tells me that not only am I moving at 5 meters per second, but I'm not moving that way in the positive, I'm moving this way in the negative. That makes it a velocity. It has both a magnitude, 5 meters per second, and a direction. I'm in the negative direction. That's what makes it a velocity. All right, we continue with a negative velocity and actually go back past 0, 0. We actually go into the negative meters. And then we have a negative velocity here. It's still a downward slope. And now we end up with a positive slope and we start moving forward again. All right, so this is information that we can get from a position versus time graph. It's not just reading the graph, but with the slope at various points, we can tell pretty much how fast and in what direction the object is moving in between those 2 points. That makes this a very useful graph for us. All right, this is one of several graphs. Our next one, velocity versus time. So we've got velocity, which is right here. You'll notice that here's my 0 point. I don't have it at the bottom of the graph because at some times we end up at a negative velocity. And as we talked about, velocities are vectors, which means the negative means sometimes I'm moving forward, sometimes I'm moving backwards. So that's why it's common for 0 to not actually be at the bottom of this graph, but we still have it evenly spaced. I also try and avoid having any breaks in here. Definitely don't put any breaks anywhere where you have data, okay? All right, let's see. Just like all the other graphs, with this being velocity versus time, the first one is our y-axis, so these are values, and they are in meters per second, and time is on the, I said y and x, I mean the vertical and horizontal. Time is on the horizontal axis. All right, we can also read this directly off the graph. At time equals 5 seconds, we have a velocity of 0 meters per second. At time equals 2 seconds, we have a velocity of positive 2 meters per second. And at time equals 8 seconds, we have a velocity of negative 2 meters per second. All right, here we go. Let's take a look at the slope. We talked about the slope last time. We can not only read what's on the graph, but we can find some slopes. Well, I'm going to make this a little bit simpler because we introduced the idea of rise over run. This is 1, comma 2, 1 second, and 2 meters per second. And this is 0, 0. So if I do my rise over run, then we would have 2 meters per second minus 0 meters per second divided by 1 second minus 0 seconds. We end up with 2 meters per second divided by second, which is the same thing as meters per second squared. That's actually our acceleration. The slope of a velocity versus time graph will give you the acceleration. Now, you don't necessarily have to memorize this, but it is useful to be aware of it. If you look at the units will tell you what you end up with. So if I have meters per second divided by seconds, those are the units of acceleration. In this case, we will get the acceleration by finding the slope here. We could also look in this region here, but we're going to find that it's a flat level line, so we end up with 0 meters per second squared, which means the object is not accelerating, which means it's not speeding up or slowing down, at least in this case, which means since we started this region at 2 meters per second, if we don't speed up or slow down, we stay at 2 meters per second the entire time. So that matches up with it. Great. We'll actually have a negative slope in here. That will be a negative acceleration. Now in this case, because we have a positive velocity and a negative acceleration, you'll see that it actually slows down. So we go from 2 meters per second down to 1 meter per second, down to 0, we come to a stop. Negative accelerations do not always mean that something is slowing down, though. You have to be careful about that. Things slow down when their velocity is positive and their acceleration is negative, or, as we're going to see in just a moment, when their velocity is negative and their acceleration is positive, they will also slow down. Let's take a look at this, because I have a negative acceleration here, and we are at 0 meters per second here, and then we start speeding up in the negative direction. So it's the same thing as me being here at 0. I have a negative acceleration. That means my acceleration is to the left, and I'm going to start speeding up to the left and hopefully not trip over anything. Hooray, I survived. That's one thing to keep in mind about this, and that's also why I mentioned before, do not use the word deceleration. It can be very tricky for students to predict when something is going to decelerate until you get used to it. Remember, in regular usage, decelerate means specifically slowing down. Negative accelerations sometimes will slow you down, but sometimes they will speed you up. It depends on which way the vectors are pointing. Another great example of that, I mentioned that you can have up being the positive direction, down being the negative. Gravity has a negative acceleration. If I have a positive velocity, I throw something up, gravity will slow it down, slow it down, slow it down, slow it down, until it comes to a stop. And then gravity remains a negative acceleration that will make it speed up as it goes down to the ground. Negative accelerations do not mean that something has to slow down. In fact, many times things will speed up when subjected to a negative acceleration. Slowing down can only be predicted if you know the sign of the velocity, basically which way it's going, and that the acceleration is in the opposite direction of whatever the velocity is. All right. Now we've got a little bit of that. We could go through here. We could find the slope in this region. Looks like it's a spacing of 1. We're at -2 to 0, so we'd end up with -2 meters per second squared. Once again, it is a vector. And since we were starting at a velocity of 0, that means the thing is just speeding up in the negative direction, not slowing down. It was slowing down here because it has a positive velocity and a negative acceleration. Here, it's going into the negative velocity and a negative acceleration, so it speeds up. Then we end up with a 0 acceleration. It stays going at -2 meters per second. And then now it will once again slow down because it has a negative velocity, but a positive acceleration. If the acceleration is one way and the velocity is another, the thing will slow down, and that's when you get a deceleration. That's the only time that happens. Negative accelerations can make things speed up. Positive accelerations can make things speed up as well. In fact, they do whenever the acceleration and the velocity are both pointed the same way, or if something is starting from rest, accelerations, both positive and negative, will make it speed up regardless. All right, enough about acceleration. So velocity versus time, we can read the graph itself. The slope will give us the acceleration in a given time period. And as I mentioned before, we have 2 meters per second here. Our acceleration here is 2 meters per second squared. Here we have 0 meters per second squared, and then we go to a negative. I can actually solve problems about what's going on here, despite the fact that I have changing accelerations. Now granted, I'm breaking them up into pieces, so we could still work with our kinematic equations if we break them up into sections where we have constant acceleration. But tying back to what I mentioned before, our kinematic equations can't solve all of this at once because the acceleration changes. All right. Let's see the other thing that we can get from the velocity versus time. You may have noticed that I only used blue for my slopes this time. That's because I'm holding on to green for the following. The other thing that we can look at is the area under the curve. And what I mean by the area under the curve, it's the area that is in between your lines that represent your motion and the x-axis, the horizontal axis, I should say. So right here, I have a shape that happens in the first 1 second of motion. What shape is this? Well, it's a triangle, specifically a right triangle, but it's a triangle. All right, it has a base of 1 second, but that's how wide the base is, and it has a height of 2 meters per second. I mentioned that I want to find the area, so area of a triangle is 1/2 base times height, and that will be equal to 1/2 base, which is 1 second, times height, 2 meters per second. Well, let's see, that's going to give me, well, 1 meter per second times second, meter. What has units of meters? Displacement. The area under the curve of a velocity versus time graph will actually tell you how far the thing goes during that interval. During this first second that an object is accelerating from rest from 0 meters per second up to 2 meters per second with an acceleration of, we found 2 meters per second squared, it goes 1 meter. In fact, take your kinematic equations and double check that. You'll find that you come up with it. If your starting velocity, initial velocity is 0, your acceleration, let's ignore the acceleration actually. Let's say your final velocity is 2 meters per second and your time is 1 second. Go ahead and solve that. We'll ignore the acceleration because we found that. We didn't get it directly off the graph. But if you use your initial velocity of 0, your final velocity of 2 meters per second, and your time interval, t, is equal to 1 second, solve for delta x. You'll find that it comes up to 1 meter. Now, the other thing that we can do is, okay, that's one small section. Let's go with the next section. We know right here in the first second, we go 1 meter. Let's find the area of this. That's a rectangle, maybe a square, but a rectangle, so we take the base, which goes from 1 second over to 3 seconds. That's 2 seconds here. And our height is 2 meters per second. 2 times 2, that's going to be 4 meters. We go 4 meters here. 1 meter, 4 meters, and then if I look over here, we've got a triangle. Okay, it has a base that goes from 3 seconds all the way over to, finding right here, 5 seconds. So that's 2 seconds, and it once again has a height of 2 meters per second. So we would have 1/2 base times height. This is 2 seconds. That would be 2 meters is how far we go. All right. Check that real quick. I'm going to check the camera. Okay. So on long recordings, I have to double check the camera. Here we go. Now we know that in the first second, we've gone 1 meter. In the second 2 seconds, we went an additional 4. And then in the next 2 seconds, we went 2 meters. You can double check all of these with your kinematic equations. You'll find that you'll get the exact same outcomes. Main reason why I mentioned before that we have trouble using the kinematic equations. We can use the kinematic equations, remember what I had you write here, whenever acceleration is constant. Well, for the entire first second, we have an acceleration of 2 meters per second squared. That's a constant value. So the equations will give us this value here. We could also solve it in this section here, where it has a constant 0 meters per second squared. And over here, we have a constant negative 2 meters per second? Negative 1 meter per second squared. I'd have to go through and actually do the numbers on that. But regardless, because the accelerations are constant in these little sections, we could actually solve a kinematic equation for the little sections. All right, enough side note on that. Let's talk about what happens over here. Now, I told you that the area in question is in between your graph of the motion and the horizontal axis, where y equals 0, whatever your y happens to be, your vertical thing. So let's take a look at this area. It's an area, it is between my curve and the x axis, if you will, but it's beneath it. My base right here is 1 second, and my height, well, it goes from 0 to negative 2. My height is negative 2 meters per second. Now that may seem weird, but we're going to talk about this. Look at my velocity. My velocity is positive over here. What does that mean? It means I'm moving to the right. I'm adding more displacement to the right. What happens here? I go to 0, so I grind to a stop. And what's the next thing? My velocity goes negative, which means I start moving to the left. Which way is my displacement? Also to the left. I start backtracking. I went 1, 5, 7 meters from the very beginning up until this point. So I'm 7 meters in the positive direction, and then I start moving backwards. When I solve for this, my area, if you will be negative 1 meter. What does that mean? Well, I was at 7 meters, positive 7, and now I displaced back 1 meter. I'm now at 6 meters. And then I continue going. Let's take a look at a small section of this. Let's go like this. I could go all the way over here, but I'm not just yet, and I'll show you why. So let's see, I've got a base of 2 seconds from 6 to 8, and I've got a height, if you will, of negative 2 meters per second. So if I do that right, that's negative 4 meters. So I went 1 meter forward, 4 meters forward, 2 meters forward. I ended up at 7 meters, and I backtracked 1 meter to 6. Now I've backtracked another 4, which puts me at positive 2. Now let's see what happens in this section when I add in this area. Well, that's 1 second, and at negative 2 meters per second, that gives me negative 2 meters right here. At time equals 9 seconds, I've gone backwards 1 meter, gone backwards 4, gone backwards 2. At time equals 9 seconds, I backtracked 7 meters. But from 0 to time equals 5, I went forward 7 meters. So I went way over here, I stopped, I backtracked, and at time equals 9 seconds, I've actually undone all the motion that I have. This entire area is equal to this entire area, not including this. At time equals 9 seconds, I return to where I started from. Most likely x equals 0, unless I give you an initial condition. I might say that we didn't start at x equals 0, we started at x equals 10. Then I went from 10 to 11 to 15 to 17, and then I went back to 16, then I went back to 12, and then I went back to 10, which is where I started from. However, I'm still moving. If I find the area of this, that's 1 second, -2, and we've got that. I'm going to finish my motion up at -1 meters. I actually pass back where I started. All right. Broad overview on velocity versus time. You can read the graph just like any other graph, but the slope will give you the acceleration. And if you find the area under the curve, you will find the displacement during that time period. So from 0 to 1, 1 to 2, 2 to 3, and so forth. If you have strange shapes, sometimes you might have something that looks like this, where it goes up at an angle, then like this, then up at an angle some more, and then maybe down like this, something like that. What I like to do is turn this into a triangle, turn this into a square. We've got a triangle here, and we've got another square, I should say rectangle. Even though this is 2 seconds by 2 meters per second, I have a hard time calling that a square because squares have the same sides. Well, they both have 2, but they're not both the same thing. This is 2 seconds, and that's 2 meters per second. So I would actually treat it like a rectangle, but that's splitting a few hairs. Many of you may be familiar with the area of a trapezoid or a parallelogram or all sorts of stuff, but to me that's just extra things to keep track of. Just cut them up into nice and easy to use triangles and squares. Now, the one thing that you cannot use this on would be a curvy line. In that case, you pretty much have to use calculus, which, unless you're in calc-based physics, we're not going to be doing. All right, that's the velocity versus time. Let's finish this up by looking at the acceleration versus time. So, the acceleration versus time, we can read the graph. We've got acceleration here in meters per second squared. We've got time in seconds. My y equals 0 is right here, so that's my axis, if you will. And we can actually find, just reading the information, at 4 seconds, our acceleration is positive 2 meters per second squared. It can go negative. That's an acceleration in the negative direction. And so at time equals 7, for instance, we get down to -3 meters per second squared. All right. First off, we've been dealing with the slopes. I'm going to go ahead and introduce this. Let's take a look at it. We can find the slope in here. It looks like we've got 2 seconds, comma, positive 2 meters per second squared. Great. Over here, we've got 0, 0. 0 seconds, 0 meters per second squared. We find our values on this, we'd end up with 2 meters per second squared minus 0 meters per second squared divided by, 2 seconds minus 0 seconds. We end up with 1 meter per second cubed. Let's talk about this real quick, just so you've got an idea. We're not actually going to work with it in class. This is a real thing, but it's not something that we actually work with, at least at this level. It's got a funny name. It's called a jerk, is actually what the name of that is. It's a scientific term, believe it or not. What this all means, when we have the position versus time graph, when we looked at the slope, we got the velocity. Now, what a velocity does is it tells you how quickly you're changing your position. Let's say in 1 second, I go only half a meter, like this. I'm moving pretty slowly. We would call that half a meter per second. If, however, I were moving much faster, maybe 2 meters in 1 second, we'd call that 2 meters per second. In short, velocity tells us how quickly we're changing our position. Also, for a velocity versus time graph, the slope tells us the acceleration. Well, the acceleration tells us how quickly we're speeding up or slowing down, how quickly we are changing our velocity. We could also look at the slope here. This concept that we call a jerk is how quickly our accelerations are changing. Is our acceleration getting big? Is our acceleration getting small? If you were an automotive engineer, you'd probably be using this whenever you look at a transmission changing gears. You all have felt that before when a car changes gears. It's like, brr, 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 and then you feel kind of for want of a better term, a jerk. It's as though you're moving, and then all of a sudden you kind of stop for just a moment, and then you start moving again. That's what happens when we shift gears in a car, and you'll find that the acceleration of the car will actually change slightly. We would, if we were going to look at that, model that with something called a jerk. We could represent it with this. That's pretty much the last time we're going to talk about it, at least in this intro level class. All right. That's the slope. We're pretty much never going to use it. What we're going to look at is the area under the curve. So I'm going to go through this quickly. We can find the area under the curve here, and we will find that, well, let's see. We've got a triangle, so my area is going to be 1/2 base times height, and then we have 1/2 times my base. Well, let's do the entire thing here. I could have done that one small section. I can do this larger section. It's however I want to look at this. 0 to 2, my base is 2 seconds. My height is positive 2 meters per second squared. When I multiply all these out, I end up with, what's that going to be? 2 meters per second. What has units of meters per second? Velocity. What this tells us is actually what you could call delta V. It's our change in velocity. Now remember, as we talked about in class, delta is specifically V final minus V initial. So if I have positive 2, that means that my final velocity is 2 meters per second greater than my initial velocity. This thing is speeding up. If, however, if we jump over here, now we've got another one of those negative areas. So I go from, let's see, this can be kind of hard to read. Looks like this is a weird graph. It's 5.5 seconds right here, all the way up to 7 seconds. So my base here is 1.5 seconds. And then my height is negative 3 meters per second squared. All right. 1/2 times base, 1.5 seconds, times height, 3 meters per second squared. Oops, negative 3 meters per second squared. Bad Sanchez. Calculator. I am very lazy at this point, so I don't want to do this by hand. You'd think I'd be better prepared. Let's hope this one's set properly. Here we go. 0.5 times 1.5 times 3. No, this is one of the bad ones. 9/4. I want real numbers. 9 divided by 4. 2.25. We end up with, now remember there's a negative here, delta V equals negative 2.25 meters per second. In other words, we decrease our velocity. Our final velocity is lower than our initial velocity, so small number minus a big number gives us a negative number. We slow down by 2.25 meters per second. Now, it doesn't tell you the actual velocity, but it does tell you what happens to the velocity. All right, one last thing that I want us to look at, just for clarity. You can find the area under the curve for a position versus time graph. Because, I mean, it's a graph. You can find areas. My base is 1 second. My height is 2 meters. If I put that together, I'll have 1/2 base times height. I end up with 1 meter second. That is not millisecond, but it's meters times second. I probably should have double-checked this. That might actually be a thing. I don't know its name. I don't know what it's used for. This is one of the things where in math classes, you can always find slopes, you can always find areas under the curve. You can do that all you want. But in the end, we only focus on things that will actually give us values that we actually want. In this case, I don't know of anything useful that this value will let us solve. So for the most part, we're going to ignore it. But who knows? Maybe someday someone will figure out if this is useful for something. 1 meter second. If that's the case, you might even end up with a Nobel Prize if you advance science, and it turns out that this could answer a problem that we don't know how to solve yet. It's happened before. Anyway, you can find the area under the curve for the position versus time, but we pretty much never will. It doesn't tell us something that we know the use of. All right, just one final thing. All right, like I said, one final thing. I needed to open up my notebook here. All right, graphs. This is something that I give out each year, and it's kind of my way of keeping track of everything that we just got across. I would recommend keeping this somewhere where you can have it handy, somewhere in your notes that you can find easily. If you have a position versus time, that's x versus t. Now remember, x represents a position, usually implied to be horizontal. You could have y if you had things moving vertically, but position versus time is represented by a lowercase t. You can have a velocity versus time, and you can have an acceleration versus time. Now, if you want to be thorough, we should put vector signs on each of these because they are vectors. Now you can read the graphs themselves, but over here I like to mark slope. If you look at the slope of a position versus time graph, it will give you the velocity. It'll tell you about the velocity. And if you look at the slope of a velocity versus time graph, it gives you information about the acceleration. Now again, this might be redundant for you. If you pay attention to the units will tell you about what you get. The other thing that you can look at is the area under the curve. Area. If you do that, the area under the acceleration versus time graph will tell you about the velocity, and the area under the curve of the velocity versus time graph will tell you about the position. Specifically, it will give you the displacement, delta x, and delta v for each of those. All right. This is a pretty useful thing to have on hand, especially if you want to be working with graphical kinematics. So I would keep track of that. Final thing that I would say is this. Slope is a reference to something called differential calculus. You'll find that each of these have a derivative-oriented calculus relationship. If you're in my calc-based physics, we actually talk about that in class and use it. The area under the curve, areas under the curve, give you an integral relationship. And that's another thing at work which we work with in calculus-based physics. But for algebra-based physics and even sometimes calculus-based physics, this is a perfectly good thing to have on hand.